Hello, everybody. We're going to start talking about one new topic in the inorganic chemistry course, which is the equilibrium in solution. And this is kind of a nice topic, but we need to give some introduction before we go into the topic and the details. To get started, we will start with what we call the law of mass action. And just to understand what's going on and what we mean by the law of mass action, let's say that we have a reaction like this one that we see here, that two reactants A and B go to C and D. And let's say this reaction or we understand from this reaction that these are the reactants and these are the products. And we also understand that the reaction goes in both directions, the forward and the backward direction, because the arrow takes this shape. If it takes this shape, then it is one directional reaction, so there is no backward reaction. But since we have this shape, this means that the reaction goes to the backward and to the forward and backward direction, which means that A reacts with B to give C and D, and C reacts with D to give A and B. So it's going both ways. And if we take a look at the concentrations as a function of time, if this is the concentrations and this is the times, and we will see that the reactants will start with a big value and the products will start with a very low value, maybe 0, because there is no C and D at the beginning of the reaction. And as the reaction proceeds, these will decrease, the reactants will decrease. And as it proceeds, the products will increase until we reach a point where the concentrations are constant. They don't change with time. So from this point, you'd see that the concentrations do not change as time increases, which means that the reaction reached its end, or what we would expect that the reaction has reached this end. It can take this shape, or it can take this shape that we see here, whatever shape, it doesn't matter. This overlap doesn't make any problem. So the point here is that if we say that the reaction ends, then this is not an accurate description to what's taking place actually. So what takes place is that the reaction reaches equilibrium. And this is pretty important to understand that the reaction reaches equilibrium, which means that at these concentrations that I reach at the end of the reaction, or the concentrations that remain constant, they perform forward and backward reactions with equal rates. So I have 1 mole going in this direction and 1 mole going in the backward direction. So it is it's actually, there is a reaction taking place, but the net reaction is 0, and this is what we mean by equilibrium. And it's important to understand how to or what's the equilibrium concentrations. And the law of mass action is the relation that can tell us what is the equilibrium concentration, or will let me know when will I reach the equilibrium, or what I expect when I reach the equilibrium. And the law of mass action is as follows. It is K, which is what we call the equilibrium constant. Okay, so this is as it's called, it's a constant, which means that it is a fixed value. It's function of temperature and pressure, mainly temperature and pressure, and it is not function of concentrations. And this is important. I'll come back to this in a minute. So this is a constant that is specific to this reaction or to this process, and it gives a relation between the concentrations of the products to the concentrations of the reactants. So I have here the products C and D, so it's going to be the concentration of C. And here when I put a name of one of the components between square brackets, I mean that this is concentration. Okay, so when I put this, I mean the concentration of C, and it's multiplied by the concentration of D divided by concentration of A divided by concentration of B. So it's the multiplication of concentrations of products divided by the multiplication of the concentrations of the reactants. So let's say if this reaction has stoichiometric coefficients A, B, C, and D, lowercase a, B, C, and D here, then A could be 2, 3, 4 fraction, whatever the value. Then this will be raised to the power of the stoichiometric coefficient. This is in some cases, it's not always the case, but let's talk about the cases where this is true. So this is C to the power of small c, D to the power of D. And if you think about it, let's say that, for instance, I have a reaction where 2A goes to B, which is actually A plus A goes to B. So the concentration of the product is B, and the concentration of reactants, I can consider these as two separate reactants. So this is going to be A multiplied by A, which is A to the power of 2, which is the stoichiometric coefficient. So that's why you put the powers here. So this is the form of the law of mass action for a reaction like this that we have written in the very beginning. There are some points that we need to keep in mind. First is that the value of K will indicate how far the forward direction or the reaction will proceed in the forward direction. So let's say that K is a big number. So this means that the concentration of C multiplied by the concentration of D is greater than the concentration of A multiplied by the concentration of B, which is even without knowing what is the final concentrations, I can tell if the final concentrations will be high or low, if the conversion is high or low. So this is something that I can understand. And the opposite, if K is small, this means that the concentration of the product is not as high as the concentration of the reactants. So this is one thing. The second thing is that I can play with, after knowing this information, I can play with the conditions to force the reaction to go into the direction that I want. So, for instance, if I know that the K is directly proportional with T, for instance, and I want to push the reaction to the forward direction, so in this case I can increase the temperature, so the K will increase and I will get higher conversion. This is true in case of endothermic reaction, because as you provide more heat, then the reaction will proceed in the forward direction, and this is because the K is higher with temperature, and the opposite for the exothermic reaction. One other thing, if for instance you can kind of mess up with the equilibrium concentrations so that the reaction would go in the forward direction. And a good example is the one that we see here for the reaction of ammonium chloride plus sodium hydroxide that gives ammonium hydroxide and sodium chloride. So this is a kind of reaction between two components giving two other components, and again the equilibrium law of mass action is applicable here. So the equilibrium constant in this case is going to be the concentration of ammonium hydroxide multiplied by the concentration of sodium chloride divided by the concentration of ammonium chloride multiplied by the concentration of sodium hydroxide. And it's going to reach the equilibrium, but at some specific conditions or at high temperatures, the ammonium hydroxide breaks to ammonia plus water, and this ammonia evaporates and leaves the solution. And in this case, what happens is that the ammonium hydroxide gets lower. So I have a decrease or depletion in the ammonium hydroxide, which means that the numerator gets lower. And in this case, the reaction would be forced to go into the forward direction until the ratio between these two, the numerator and the denominator, it satisfies the value of K. Sometimes it's used in some reactors. You would have kind of membrane or something that will extract one of the products so that the reaction proceeds in the forward direction. So it's important to understand the concept of the law of mass action, and to understand how it's important for us to know that the ratios, and how to manipulate it to achieve something that you want to do, or to get in from this reaction. So I'll stop here and we'll continue in the next video, inshallah. Goodbye.